Okay, welcome back. So today we're going to talk about angle-angle similarity in triangles and how that helps us. Okay, so we've talked about this before. Similar figures have the same shape, but they're different sizes. Now, if two triangles are similar, it means that their corresponding angles are congruent and the lengths of their corresponding sides are proportional. So first let's go over the angles. So we know that if this is a dilation of, if the primes are a dilation, if this triangle to the right is an image of the triangle to the left under a dilation, then we know that their angles are equal to each other. I can literally bring this up over here and show you that these angles are equal to each other. Okay, so note that the angles are congruent. That's going to be very helpful to us in a second. But we know that even though their corresponding side lengths are proportional, that means that corresponding sides are the sides that relate to each other. So BC has a corresponding side, B prime, C prime. So B prime, C prime is the image of BC under the dilation. So it's a corresponding side. Okay, we know that they're not equal to each other, but we do know that when we measure them, their ratios are going to be the same. So for instance, if I take this ruler and I measure this side length, so this side length, A prime, C prime is about 7. So A prime, C prime is equal to 7, and this should be millimeters, okay, according to our scale on this video. Okay, and if I measured AC, this is about 3.5, okay? So AC is equal to 3.5 millimeters, okay? And if I divide these, I get 2. Now, this is going to be the same thing if I took this measurement and I flipped it around. Let me see if I can flip my, okay. And I measure the side length, AB is going to be 4, and A prime, B prime is going to be 8. So let's pick it back here. So if I say that A prime, B prime is equal to 8 millimeters, and AB is equal to 4 millimeters, and I divide them, then I also get this ratio of 2. So that's what it means to be proportional. That anytime I take the image's length over the pre-image's length of the corresponding sides, I always get the same proportion, the same ratio. Okay? Okay, but what we're going to use is we're going to use the idea that in similar triangles, all the angles are equal to each other. All right, but what's nice about triangles is that we actually know that if two angles of one triangle are congruent to another triangle, then the triangles are similar. Okay, so what we're doing is we're using the reverse. This says that similar figures have congruent triangles. We're saying that if similar figures have congruent angles. What we're saying here is that if all angles are equal to each other or congruent, then we know that the triangles are similar. So can we prove that these two triangles are similar? Well, first of all, we're going to need the angles. Now, this one says 135, but I know from the angle sum theorem that if I take this and I add them together, I can get the missing angle. That's 135. Now, I know that 180 minus 135 is going to be, let's see, that's 10 and 7, so 5 and 4, that's going to be 45 degrees right here, okay? And if I add these two angles together, I get 145, so the missing angle here is 35. So actually these figures are, these angles are similar to each other, it's just that angle B and angle E correspond to each other, angle A and angle D correspond to each other, and angle C and angle F correspond to each other. So I can say that, and be careful how you are writing your triangle. So if I say triangle ABC is similar to triangle, and notice that I have to name D first, triangle DEF. So you have to make sure that the thing that you name first is always the angle that's similar to the corresponding angle. And the angle that you name second is corresponding to the second one in the when you write it, the second triangle down. And likewise for the third one. Okay. So here I can read off, I can infer that C is congruent, angle C is congruent to angle F, angle B is congruent to angle E, and angle A is congruent to angle D. Now, What I know is that I didn't even actually have to find this, this one right here. Okay, the angle postulate, notice that it's AA, it's not AAA, says that if two angles are congruent, then I know the triangles are similar. And this is the reason why. If I know that two angles are congruent, so for here, if I know that these two angles are congruent, then I know that their sum is going to be equal to each other, and that means the third one has to be 35 because of the angle sum theorem, right? All angles add up to 180 degrees inside of a triangle. So if two of them are congruent, then I know the third one is. And if I know all three angles are congruent, then I know the triangles are similar, okay? Okay, and the way that we can use this in a real life situation is by creating, making similar triangles to solve problems that we need. Okay, so while playing tennis, Matt is 12 meters away from the net. So notice that this is Matt right here. Here's the net, and he is 12 meters away from that, okay? And the net itself is 0.9 meters high. He needs to hit the ball so it just clears the net. So if he's playing tennis, he wants it to hit and strike right in front or right in back of the other player that's right here, right? He doesn't want to hit it so that it strikes here, for instance, because then the other player can hit it with he or she's tennis racket. So he wants to hit it so it sort of goes straight down into the ground, right as it passes the net, it goes right into the ground, but it has to clear the net, right? If it gets caught right before the net, it's a point for the other player, in some cases. Okay, so he just wants to clear the net, and he needs to hit the ball so that it just clears the net and lands 6 meters beyond the base of the net. So this has to be 6 meters, right? So that's what we know so far. At what height would Matt hit the tennis ball? So we are looking for this right here, okay? Now, what we know absolutely is this larger triangle has, let's see the triangles that we have. Okay, so there's actually two triangles in this figure. We have this tiny one right here, and we have the larger one. And actually maybe it's not so helpful to use a highlighter there. Let's just look at, let me outline it with pen. Okay, so here we have this triangle right here. Okay, and then we have the larger triangle right here. Okay, so let's see if I can pull these away here. Okay, here's the larger triangle. Whoops. And we have the smaller triangle right here. Okay, so what we know is that the two angles right here have to be equal to each other. Let me pull this up a little bit. Whoops. Okay. We know the two angles have to be equal to each other because one was inside the other. So that we know that these angles are equal to each other. And I can mark them with a single dash line along this little curved line that I created. So we know those are equal to each other. We know that these are equal to each other because they're both 90 degrees. So if two angles are equal to each other, then the third must be equal to each other. And these triangles are similar, which means that they create proportional relationships. So if this is 6 meters right here, and this is 0.9 meters, and I know that this whole thing is 6 plus 8 meters, which is 18 meters. So the length across this bottom one is 18 meters, and I'm wondering what this is, then I can create a proportion here. So I can say 6 is to 18, right? 6 is to 18 as 0.9 is to this unknown value, right? This side is the ratio of this side to this side is the same as the ratio of this one to this one. And now that I have a proportion, I can go ahead and solve. 6 times x is 6x. 0.9 times 18 is, this is equal to 16.2. Okay, and if I divide each side by 6, I would get x is equal to 2.7. Right? And so that would be 2.7 meters. So we determine the height that he needs to hit it at by using similar triangles. This would be 2.7 meters. So he has to hit it at 2.7 meters above here. Okay. Okay, now I want to show you why we can use similar triangles to explain why it doesn't matter which 2 points we use to find slope, that the slope is always going to be the same on a line between any 2 points. The first thing I want to do is draw a line. Okay, then I want to draw some points on line A and B. See A and B here. And I want to draw some points C and D. So you'll notice that A and B are much closer together than C and D are. And I want to measure the slope between C and D and A and B. Now remember, slope is rise. It's the ratio of rise to run. So basically what I want to do is just take a horizontal line right here and draw it from C, and take a vertical line and draw it from D, and have them meet at a right angle. And I want to do the same for B, A and B. Okay. Now, what I want to know is I want to know that this rise over this run is the same as the ratio here to here. Okay, so that's what I'm looking for. Let me take away these things so it's a little easier to see. Okay, now in order to do that, I have to show that these two triangles are similar to each other. Okay, now to show that they're similar to each other, what I want to do is I want to extend the line that I first drew and extend the sides of the triangles here, so that what you can see is that, let me highlight this real quick. This line that I drew initially is a transversal to these lines right here. Okay, we've talked about transversals before. Now, if these lines are transversals, then what you'll notice is that these angles right here are corresponding angles. Okay, so I'm going to mark them with this purple pen. These angles are corresponding, which means that they are congruent to each other. So I'm going to mark them with 1 dash here, meaning that they are congruent. All right. I also know that this is a right angle and this is a right angle. So right now I have angle, angle, and it means that this third one is automatically congruent to the third one up here. And that means that these triangles are similar to each other. So let me actually put another point in this triangle so we can talk about it. It's A, B, and we're going to have to call this one E for now. I know that's a little out of our naming habits, but since we named this one C and D, let's name this one, actually, you know what? Let's name this one Z. So we have Z, A, and B. So it's like we wrap around the alphabet, and we can name this one E. Okay, so it could be C, D, and E. So it's okay. Okay, so we know that triangle ZAB is similar to triangle ECD. Right? So Z and E are corresponding angles, so we have to make sure to write them in the same order that we have to write the second one in the same order in which we wrote the first one. We have to write the corresponding angles in the same order. Okay, we know that those two triangles are similar. Well, if we know that they're similar, then we know that the ratios of their corresponding sides are equal. Well, that means that DE, the side length DE over the side length CE, right, which is just the rise over the run, that's going to be equal to side length BZ over side length AZ, right? Which means that the ratio of rise to run is the same, which means that the slopes are the same. Okay, so that means that this line right here has the same slope along this portion of it as it does along this portion of it, leading us to the assumption that we made all along when we were graphing lines, that it doesn't matter the points that we choose, the ratio of rise to run is going to be the same between any 2 points. That's what marks a line from a curve, right? A line has the same rise over run, it has the same slope all along the line, so that the rate of change is the same all along the line. It's constant, as opposed to a curve where the rate of change changes between any 2 points. All right, and that's the end of the lesson for today.